So if you remember when we started our explorations of magnetism, one of the things that was observed was that if you took a bar magnet, it always had a north and a south end. And even if you cut it in half, what you ended up with was two bar magnets, each of which had a north and a south end. And then you could take one of those magnets, cut it in half, and so forth. Now, I asserted that this actually happens all the way down to the atomic level. That even when you get down to individual atoms, they still have a north and a south end. So this means that our atom must have a magnetic dipole moment. So I'm going to draw the nucleus of an atom here, and I'm going to go ahead and assume that our atom has a upward pointing magnetic dipole moment. Now it turns out that there are three major contributions to the magnetic moment in an atom. Actually, two big ones and one small one. One of the two big ones is the motion of the electron orbiting the electrons orbiting the nucleus, in particular the valence electrons. So let's go ahead and draw ourselves an electron right here. And we will imagine that this electron is moving around the atom like so. Yeah. So if you think about that, if our atom is moving, if our electron is moving this way, and this is, to be fair, a semi-classical picture. Quantum mechanically, it's a little weirder than this, but it's still the same basic idea. Let's try to draw a better thing here, though. There we go. So semi-classically, what we can argue is that this means we have a conventional current going like this around our nucleus. So again, if we do the hitchhiker rule and you put your thumb along, your right thumb along the direction of the of this current, it's a current due to a single electron, but hey, it's still a current. You see that the magnetic field inside the loop has to point up. Thus, we have an upward pointing magnetic dipole moment due to the orbital motion of the electron. So I will write this as orbital. Now, it turns out, though, that there is, so this is one of our two big ones. This is the orbital magnetic moment. And this is just due to the electron, the valence electrons acting like a current loop. So there is another major contribution, and it's on the same, it's about the same size, and it's what's called the spin magnetic moment of the electron. If you've had some prior exposure to chemistry, you may have heard about electron spin. So I'm going to go ahead and tell you pretty much everything we know about electron spin, and you're going to be profoundly disappointed. We don't know that much about it. We know that this is some sort of intrinsic degree of freedom of the electron, and it's measured in units of angular momentum. Disappointingly, though, it almost certainly isn't actually physically spinning. Very careful electron-electron scattering experiments that were meticulously spin polarized that would show up differences in scattering if the things were actually spinning around are suggestive that it isn't actually spinning. There's something else going on, and it's an inherent property of the electron. Now, because this has an electric charge, we wind up having an inherent magnetic moment associated with this. So, the one other thing that I can mention about spin is it does tell us some things about the symmetry of the particle. So you may have heard that an electron is spin 1/2. So what would that mean? We can start by thinking about what a spin 2, an example of something that spin 2 might look like. If something is spin 2, it has the property that it looks like itself again after you rotate it 1/2 of a turn. So I'm imagining here that we were thinking about, like, say, a face card in a playing card deck or something like that. So, I don't know, maybe the Queen of Diamonds or something like that. If you take a card like that and you turn it through 1/2 turns, it looks like itself again. And particles that have that kind of behavior are spin 2. There are other cards in the deck that are spin 1. For instance, the Ace of Spades. Yeah, that's working out real good. So the Ace of Spades, and I'm not going to try to draw little spades there. The Ace of Spades will only look like itself again if you take it through one complete churn. So I'll write this as 1/1 churns. And we'll say this is a particle that has this kind of a symmetry. There we go. Particle that has this kind of symmetry is spin 1. So again, it's 1/1 churns. So what would spin 1/2 look like? Well, the playing card analogy breaks down horribly. Whatever it would look like, it would be something that if you rotated through one churn that wasn't, if you rotated it through one churn, it wasn't good enough. But if you rotated it through 2 whole churns, it would look like itself again. So a spin 1/2 particle is one that looks like itself not after one complete churn, but after 2 complete churns. Now, believe it or not, there are actually examples of this in nature. For instance, the way that your shoulder and the musculature of your shoulder and elbow work. You can actually take like a glass or a glass of water or something like that, and with some practice, you can go ahead and cupping your hand under the glass of water, you can churn it around through one churn, and then you'll have to hike your arm up as you're going around, but you can do a whole second churn and get back to where you started from. So in one churn, your arm necessarily lifts, and then two churns, it goes back down. You can do some Google searches for water glass trick or things like this. It's also known as the Balinese dancer trick. And so this is an example of a part of your body that has spin 1/2 symmetry, where it looks like itself after two complete churns, but not after one complete churn. So there you go. That unfortunately is pretty much just about everything we know about spin. We don't know a whole heck of a lot. But whatever this property is, if when the electron is charged, we've got this angular momentum measured quantity, and that seems to bring with it a magnetic moment. And this contribution is just as significant as the orbital contribution. Now, sometimes the spin and the orbital contributions will reinforce, and other times they'll cancel. If they cancel, there is a weaker thing that might leave you with something. That's the nuclear magnetic moment. The protons and the neutrons both have spin, and thus magnetic moments. But these are a lot weaker than what's due to the electrons. So it's only if we get a cancellation of the spin and orbital bit that this nuclear part will even really show up, unless you're doing very high precision spectroscopy. Now, you might be saying, wait a minute, neutrons are neutral objects, but you're still saying they have a magnetic moment? Yeah, they do. It's because protons and neutrons are actually made of things. These things have the name quarks, which you would like to think was named for the German word for yogurt cheese, but it isn't, sadly. It's instead named after it's a reference to a line in James Joyce's novel Finnegan's Wake, where a seagull is flying overhead looking at a milkman doing his rounds, and speaking in Irish dialect says 3 quarks for Master Mark, 3 quarts of milk for Master Mark. Yeah. Anyway, it turns out that protons and neutrons get made of combinations of 3 of these quarks. With a proton, you have 2 what are called up quarks and 1 down quark. They both have electric charges and spins, and thus magnetic moments. And same thing with the neutron. The neutron is 1 up and 2 down quarks. Now, it turns out that the electric charges on that combination of quarks cancel, but they have charges, they have spins, and they have magnetic moments. And so, believe it or not, you still have a magnetic moment associated with the neutron. Anyway, the magnetic moments from these protons and neutrons will add up, and they will give a rather weak magnetic moment that isn't anything really to write home about, but will show up in high precision spectroscopy. So, do want to kind of finish up thinking about, like, what if you pick up a nail with a magnet? How does that happen? Or any other piece of metal. So what's going on there is a thing called ferromagnetism. VRRO, magnetism. Magnetism. There we go. And so if you have a demagnetized piece of, say, soft iron, if you look at the iron nuclei in the lattice, and I'm not going to draw too many of them because life is short. What the deal is that initially the magnetic moments of them are pointing any old which way whatsoever. They're all pretty much totally random. Now, so what happens if, say, then we apply a magnetic field, say from a bar magnet or an electromagnet or something like this. So let's say we put a magnetic field through here. Well, the thing is that any adjacent atoms would like to have their magnetic moments align, but it's a big game of you first, no you first, no you first, no you first. But if we put in an external field, that breaks the tie. This one here will decide that it wants to match its, actually it's probably going to be this one. Let's make it a little more here. Let's look at actually these two. This will be a little more obvious. This one here will decide, you know what, you are more closely aligned to the external field. So it will be overall in a lower energy situation if I make myself align with you. Not with the external field, but with this one. So what will happen is this adjacent atom will now match its magnetic moment with the one that was more closely aligned with the external magnetic field. And then the same thing will start to happen as we go along. Maybe this one will then next decide it wants to align and so forth. What you wind up doing is you start creating what's called a domain. So within the domain, whichever magnetic moment was the one that was most closely aligned with the external magnetic field, that's how all the moments in that domain are aligned. Now let's say in some other area, you might have a domain, say, that's doing something like, in this region here, all the magnetic moments ended up, say, doing something like, I don't know, this. It was just horribly aligned right in this area. Well, again, when we're at the boundary, now we have all these domains are much more closely aligned. So at the boundary, this domain will grow because it's better aligned than its adjacent domains, and the less well-aligned domains will shrink. Now, somewhere in all of this mess was one atom that just by sheer fluke happened to be aligned with the external field. That one created the domain that will eventually win, and so then your piece of soft iron, for instance, will eventually have all of the magnetic moments aligned with the external magnetic field. Now, this process does have a limit, and this is why I keep mentioning soft iron. If you have a crystal structure, the crystal structure turns out to be too big of a gap to have domain growth jump across. So domains are limited in expanding only as far as crystal structures within the metal. So if you have a lot of small crystals in a metal, it's not going to be particularly magnetic just because the domains don't have any room to grow in. But if you have, say, soft iron, which is basically just one giant crystal of iron, then you can grow out the domain across the entire object. So that's why you can induce magnetism into, say, a nail by making it come into contact with a magnet or sticking in an electromagnet or something like that. you'll align all the magnetic domains very closely with that external field. Alrighty, so in the next series of videos, we will go ahead and take a look at electromagnetic induction, and then we will start to realize that there is interrelationship between electric and magnetic fields. So see you over there.